Okay, right. So thanks, Kell. I'm going to make a tiny correction to you because although this is about a dynamic object model within Unix processes, it's really about finding the objects that are already there, so rather than putting them in. So I'll explain what that means in just a sec. So here's a picture of what our computers were supposed to turn out like. This is a Xerox Alto. It's running a very nice high-level language called Smalltalk. And it turns out that that's all it runs. So the actual implementation of Smalltalk here is pushed right down to the microcode. So there's no sort of baggage. It's a Smalltalk system. That's what your computer does. So that was a nice vision. But something else has happened, right? So we don't just have computers that run one nice high-level language in a very uniform way. Instead, we have a very fragmented ecosystem. We get so used to it, we don't even think about it. The fact that, we have different languages and even different implementations of the same language, and that really fragments, what tools we can use, what code we can use. It just means that our ecosystem is a lot more complicated. And also, we've not got rid of these guys, right? So this is Ken Thompson and Dennis Ritchie, and the creators of Unix. And Unix, the abstractions are still alive, right? Any real system we have, we build it on top of a Unix-like operating system, whether it's called Windows or Mac OS or actually something that sounds like Unix. And there's a lot of code that's not written on any virtual machine. It's just targeting directly basically this lightweight abstraction of the machine that Unix gives us. So that stuff is still here, and that all adds to the complexity that we currently deal with. So I'm going to claim, maybe contentiously, that language VMs have failed because none of them has won, right? So we have this big fragmentation effect that I talked about, and also we haven't got rid of the Unix-like abstractions that, in the early days of Smalltalk, people were hoping we were going to get rid of. So the end result is a lot of fragmentation, a lot of complexity. This is things like, you write a program in Python, but you end up writing bits of it in C, and then you don't have a debugger that can deal with both the Python and the C, and then you have to write a lot of wrapper code to make all this stuff integrate. So that's the kind of complexity I'm talking about. So what I'm proposing in this paper is that we try a really different approach, which is to say, okay, we've got this Unix thing, we're stuck with it. So how can we evolve it so that it becomes a platform that actually supports and enables different language implementations, different virtual machines to coexist and integrate with one another? And my hypothesis is that it's possible to do this without throwing away our existing virtual machines. We just have to change them a little bit. And similarly, we won't have to throw away our existing Unix-like tool chains, like our C compilers. We'll keep them, and we'll change a few little things around the edges. And hopefully I'll convince you that this will or might work. So we can make a little list of things that are missing from Unix. And one of them is any kind of notion of object. We have this very coarse-grained thing in Unix called a file. And nowadays in Unix, that's kind of unified with a coarse-grained chunk of memory. So the subsystem of Unix that deals with memory mappings is kind of closely related to the one that deals with files. So there's an idea of really big objects in Unix, but the Unix operating system doesn't really know anything about the smaller objects that actually our programs are actually manipulating and that mean the most things to our users. So that's one thing that's missing. Another is that we don't have any kind of semantic information. To Unix, everything is just bytes, right? We have memory mappings that consist of bytes and files that consist of bytes, and that's about it. So we don't have any semantic metadata that you could call, and in this talk I'm going to sometimes call type information. That's a bit of an abuse because this word type is probably overloaded. I have a whole essay about that. I admit that I'm being a bit sloppy here, but it'll make things a bit easier. And then finally, there's this idea that if you give me an object, it'd be really nice if I could get some metadata for the object really efficiently. So this is like in Java, if I have an object, I can get its class very efficiently. And similarly, we might sometimes want some metadata about an object and then go back to the object itself. So maybe objects in some systems have names, and we can map down from the name to the object. So that's something that Unix doesn't really give us, at least not in a very complete way, and I'll say a bit more about that. So the quick summary of the talk and the paper that's behind it is I built this thing. It's called liballocs, and it adds these things to Unix processes. So it has this core abstraction of allocations, and we can think of allocations as a generalization of the memory mappings that I talked about. So memory mapping is a big allocation, but within a big memory mapping, you have lots of smaller allocations, and there's a kind of hierarchy to that. And the leaves of the hierarchy are actually the user meaningful chunks of state, like little objects, or maybe even the fields within objects that actually mean something to the user. So that's one thing we have in liballocs. And we can think of it then as implementing a kind of meta-object protocol over these allocations. And it's unlike a normal meta-object protocol within a kind of, say, Smalltalk VM, the idea is that this protocol is implemented for any object across your whole process. It doesn't matter what language it's in, what VM it's in. It could be in native code. we should be able to, these operations should be available on any of these allocations. And I mentioned part of the protocol is that we have this type metadata that I'll show you in a second. And all of this is actually based on finding the rudiments of a virtual machine inside the existing Unix systems that we have. So it's like I'll show you some examples later, but we're looking for the rudiments of a VM that are already there in Unix, and we're trying to draw them out. So that means that we can end up being very compatible with what exists already, and also brings out some kind of generality properties. So I thought I'd show you the applications of the system before I show you how the system works, just because it helps make things a bit more concrete. So here's one application. This is a bit of C code, and it's actually from Git. Anyway, it's from Git. We all know what Git is. And you can see I put a handy new line in there because there'll be something to go in there in a second. But you see that there's a pointer cast in the middle of this code. So it's taking this pointer called obj, and it's casting it to a struct commit. And so the programmer said, yeah, I know that this pointer really points to a thing with this property, a thing that is an instance of this struct. And as we know, this being C, traditionally, the compiler just trusts us, and so we might, if we get it wrong, our program crashes horribly. So it'd be nice if we had a slightly more virtual machine-like operation available here that lets us reflect on what this obj thing is, so we could do some kind of check at runtime. So one of the applications of the system I'm describing, this is the most mature application, is that we can actually write a little is-a predicate using the meta object protocol to say, okay, well, let's just check that this obj really is an instance of struct commit. And you see I've reified the data type struct commit inside an object at runtime that's got this funky name, unique type commit. Anyway, that's just a reification of the structure type. So we can assert at runtime, yeah, okay, we've got to make sure it really is an instance of this struct. So that's basically taking a virtual machine-like service and building it into Unix in a way that wasn't there previously, so that in this case, native code can take advantage of a service that wasn't there before. Here's a slightly different application. So you might know that there's this JavaScript implementation called V8, and it's embedded quite often in this thing called Node.js. So Node.js lets us write JavaScript code in a nice sort of dynamic, sort of rapid prototyping form, if we want to code that way, against, well, we get to write lots of JavaScript code. So what I've done is we can, using liballocs, we can actually extend Node a little bit. So what we can't normally do inside the JavaScript code is just access native code that's existing in the system already. So there's a printf function, but normally we'd have to write a bunch of wrapper code in C++ just to bind that thing into the JavaScript world, and then we could use it. But what I've done with liballocs is we'll say, okay, just all the objects or the liballocs knows about are just bound in to this JavaScript process object automatically. So I added this LM object hanging off the process object. LM stands for link map, so that contains all the global variables in my whole process. So here I can just say, okay, that includes printf. Printf is a function. We can think of it as a global variable. We can just call that thing, and it just works, right? So we didn't need to do any wrapper code. It all just uses the meta object protocol internally. This is a small extension to Node. And we can do slightly more ambitious things. So we can load a library. This is just sugar around calling the normal Unix dynamic loader. We can load some library called libxt, and I wanted to write myself a retro X11 GUI application. So you can do something like this. This is kind of overkill, but it's basically just doing the normal GUI calls that you would do to make a simple dialog with a button on it and run the event loop. So that's another thing we can do with this meta object protocol. And note that this is not just a case of bridging JavaScript and C, right? This is saying there is an object space in my process, and the language that we view that object space from is kind of a secondary thing. The most important thing is that there is this space of objects that liballocs, this runtime system, is tracking for us. Here's another application. So if you've ever debugged a C program, you know it's kind of annoying when you have a pointer to something, but all the debugger can tell you is that it points to void. So here we say, okay, it points to something, but the debugger, because the debugger is kind of normally only consuming information that comes from basically static information gathered by the compiler. And at this point, the compiler didn't know what's on the end of this pointer. So the debugger just says, well, it's a pointer to void, or const void in this case. So it'd be nice if we could just ask, using, again, the meta object protocol, we can ask, what is the type of the thing here? And using liballocs, we can do exactly this. And it says, okay, it's this reified type thing, like the one I showed you earlier, that's called input parameters. So then, okay, now we can continue debugging, because we can cast that pointer to the struct type that input parameters corresponds to, and then we've suddenly got access to the object that we previously couldn't print out. And yeah, making this actually nice and properly integrated with GDB is a future thing, but this already works pretty well. And finally, So I mentioned that Unix unifies files and in-memory data to some extent, and the call that really puts that into effect is mmap. So you can memory map a file, and now it's in the memory space of my program, which is great, right? So we kind of unified on disk and in-memory state. Except, of course, as I mentioned, files are just bytes, so that's not very useful because we have to write lots of byte twiddling operations. So instead, what would be nice if we could view this file mapped in memory as if it was a heap of allocations, right? Because internally the file itself has some structure. And we think about those structures as objects in memory, just much like if we viewed our malloc heap as a bunch of bytes, it would look kind of like a binary file format, with pointers going this way and that way. So actually unifying those two in a way that provides some of the user meaningful abstractions, like here the fact that this is another Git example. So Git cache is an on-disk format that Git uses as a binary format. So what we want to do is be able to treat files as heaps of typed allocations. This is only one of the 4 applications that I don't have working yet, but I thought I'd show you because it's all part of the grand plan. Okay, so I mentioned that if we're going to make this work, we need to sort of draw out the VM-like rudiments that are already there in Unix, and I made a little list of these. One of them is dynamic loading, so we can load code into our process at runtime. Another is then being able to compile that or recompile that somehow. So typically, if we're a VM, we load some high-level representation like bytecode, and we compile it down. Another is dynamic binding. So as we know, we want to be able to create when we create bindings to objects in a very dynamic fashion. Reflections, we want to be able to get metadata back from the objects that we're manipulating. And then finally, garbage collection. So there's stuff about all of these in the paper. I'm mostly going to be talking about dynamic loading in this talk. So I don't know how many of you know this API, but it's pretty well known that in modern Unix, you can actually load code into a process dynamically and use this little API to do so. So we can think of this as binding from a little bit of metadata, which is here the name. So I'm giving this API the name seal. I'm saying, please look me up a function whose name is seal. And this works. This is just standard sort of Unix as of the sort of late 80s, I think. You can also do the converse, which is you can say, OK, I've got this pointer, but I don't really know what it's pointing to. And there's actually a call that you can use to get more information about what it's pointing to called dladder, which is part of the same API. So we can say, OK, tell me a bit more about this pseal thing, this pointer that I've got. What's it pointing to? And it filled the structure with information. And so the information includes the fact that its name is seal. So that's kind of a start. That's a bit of a VM-like thing in our Unix process. But unfortunately, it only works for static objects, so basically objects known to the dynamic loader. If we pass it a stack pointer, say what's on the end of this pointer to the stack, or a heap pointer, what's on the end of this pointer to the heap, it just won't be able to tell us anything. So, another thing is debugging, right? So we know that we can do some kind of reflection in Unix because we have debuggers. So this is just a traditional invocation of the C compiler on a hello world program. You can see that we've added the -G option, which says, please generate me some debugging metadata. And then we run the debugger, and the debugger says, oh, yeah, I read some metadata from that file, and now I'm ready to go. And then we can reflect on it in certain ways, right? So the information is actually quite detailed. It will say, OK, it tells us about the source files, and it maps from addresses to source locations. It also tells us about the data types in our program, and so on. So just very quickly, I use that information an awful lot in the implementation of liballocs. And for those of you who know this paper about mirrors by Gil Brack and Dave Unger, it turns out that Unix debugging has followed these principles for ages. Right? Since before these two authors identified them, the same principles are actually at work in how Unix does debugging. So I'll show you the meta-object protocol of liballocs. It's this, I mentioned it has this notion of data type or unique type, has a notion of allocator, and we have some operations where we can get the type of an allocation, we can get which allocator allocated it, and a bunch of other things like where in the code and its space and limit and so on. And I'm showing this API in C, but again, I want to emphasize this is not doing stuff for C. This is doing stuff for the whole process. This happens to be an API in C onto those abstractions. So I mentioned that we have this notion of allocation that Unix is very coarse-grained, but in liballocs, we actually have a hierarchical structure to it. So that we can think about allocations as residing in a tree. So at the top level, we have the very coarse-grained allocations that we get from the operating system. We have memory mappings. Also, I didn't put it on here, but we could include the stack here because there's a stack allocator the kernel gives us. And underneath those, we have other allocators like liballocs that gives us smaller chunks, and then underneath those, we might add our own allocator. So internally, liballocs is maintaining this structure. It's tracking this structure so that it knows where in memory different allocators are working, and if you give it a pointer, it can figure out which allocator allocated it and then dispatch to that allocator's implementation of the meta protocol. Very quickly, I mentioned that we have a reified representation of data types. It kind of looks like this. This is, for my favorite example of an ellipse data type. Basically, we reify all the different data types here. So we have double, we have the point that's inside the ellipse, and we have the ellipse itself. And these edges represent the containment relationships between these data types. So an ellipse contains a point, and it contains a double. And there's a lot more information in there that I've not shown you, but it really tries to capture all that stuff. And this is generated by basically compiling the debugging information that the compiler gives us down into a more minimal and less redundant representation. So I mentioned that we want to be really compatible. So there's really two kinds of compatibility we care about. One is taking our existing Unix-like tool chains, like our C compilers, C++ compilers, Fortran compilers, whatever, and actually making them work with liballocs so that this meta protocol is implemented and implementable for them. And the way we do that is augmenting the tool chain. So we add a few little bits and pieces here and there. Mostly we just use the existing compiler as it is, and that kind of works pretty well. I'll show you a picture in a second. And the other case is existing language VMs, right? So I've got languages implemented as VMs, like JVM or Python or Smalltalk or JavaScript, whatever. And then we want to retrofit those so that the allocators and all the other stuff, the notions of data type that are embedded in there, they kind of map down into the liballocs abstractions so that the same APIs are available. So that's kind of mostly future work, but I can tell you more about. I've thought about it quite a lot, so I can tell you more about it if I get time. So I said I'd show you the augmented toolchain. So here's what your toolchain for traditional Unix-like compilation normally looks like, and you have a bunch of source files. You compile them. You get some binaries. You also get some debugging information, and there's some stuff already on your system, like maybe using some shared libraries. They're already there, and then you grab all that stuff and you load it and link it, run it, and then you get a process image at the end that runs. So what we do is just add a bit of extra processing around that. So we generate a bit more metadata for the stuff, basically stuff the debugging information doesn't tell us about. We generate some more metadata with a per language front end. There's like a compiler wrapper. In the case of C and C++, mostly it just generates information about allocation sites. Turns out to be pretty important. And then we merge that all together, do some post-processing to turn it into the efficient representation that I showed you. Then we load that, and then that's available at runtime for the liballocs runtime to show to the user. Very quickly, performance figures. So these are some Spec CPU 2006 benchmarks, and this is just showing you how much the compiler wrapper and all that stuff slows us down. The answer is normally not very much, but there's a couple of cases where currently it's a little bit slow. So if the column you want is the one to the left of the double bar, so it's the percentage slowdown of liballocs. Mostly it's in the sort of range 0 to 10%, and there's a couple where it's big. I can tell you why. Basically, GCC has a huge allocation rate, and so the way that we're tracking metadata in the current implementation is not very good for that, but I have some ideas for how to fix it. Last night I got it down to about 60, but I didn't put that on the slide. Anyway, I could do a lot better than that. So normally the overhead is pretty low. This is for the toolchain extension, compiled code, and so on. And then I mentioned that the other case is retrofitting existing VMs, so there's a little shopping list here. I probably shouldn't go through it in too much detail, but basically it's what you'd expect. So you have to generate these reified data types. They need not correspond directly with the notion of type in the language. That's kind of a subtle point that you can ask me about later. Then you have to implement this meta-level protocol. So you've got some allocators in your VM already. You want to wrap this protocol around them, and there's some prefab sort of support chunks of code in the library already to help you do that. If you have a JIT compiler, you kind of want to expose that code into your to your dynamic loader exactly the same as if it was loaded in dynamically from disk. So I have a little helper library that can help you do that. That's, again, I can tell you about that later. And finally, the hard part is actually making this whole process binding thing work. So I showed you the example with Node.js, where actually any object, the native objects were there in the object space, you could bind to them. Your JavaScript objects were there, you could bind to them. And the idea here is really that you can get it going just by adding an extra slow path in your, say you have a JIT compiler, extra slow path to the code you generate, which is saying, okay, if I don't know how to deal with this object, I go via the meta object protocol. So I just basically do an interpreter style implementation where I'm calling these individual operations to get the type of the object I'm dealing with and then manipulate it, consuming the description. And then you can keep your existing fast path, which is whatever's optimized for the particular object representation you're using. I've gone through that a bit quickly, but I'm happy to talk about it later. So just to wrap up, we have a core runtime and the toolchain extensions that I showed you. That works pretty well. I gave a similar talk a few months ago at ARM in Cambridge, and I found out later that they didn't believe that my stuff worked. So let me just say it really does work, and I can show you later. So the next step is to actually do this retrofitting that I talked about to make the VMs actually run on top of liballocs in an integrated way. And that's going to enable a whole bunch of cool stuff. So we can have whole process reflection, whole process tools like debuggers and profilers, and we can actually do interop without FFIs in a more seamless way. The node thing that I showed you earlier, it does work, but it has a few limitations. For example, passing JavaScript code as a callback to C code, that doesn't currently work, but it will work. I've thought about it a lot. So yeah, code's on my GitHub. If you're interested, please get in touch. I always like hearing from people. And thanks for listening.